All right, moving on to where is this actually located in the brain? To introduce this, let's think about texting. Have you ever been texting someone, maybe someone you like and you're just getting to know, and you both respond really quickly, really efficiently? Chances are you're going back and forth really quickly, you're in sync, and you're probably covering a lot of conversation topics pretty quickly, right? You're developing a strong bond with each other. Compare that to when you're just really not clicking with someone. You're out of sync, you don't tend to respond at the same time. Maybe their responses take days, and so having a conversation isn't really efficient. Which relationship would you invest in? Which person is easier to talk to? Now, pretty obvious, probably the one you're in sync with, right? So you can think of this concept of long-term potentiation sort of like your long-term partner. It's when you have an enhancement of communication between two neurons that results from their synchronous activation. So we keep talking about how almost all processes emerge from patterns of connections in the brain, right? Memory is no different. Forming new memories requires changing connections the neurons make with one another at the synapse level. So if two neurons fire at each other a lot and they tend to link up and communicate often, that connection is then going to strengthen. So for instance, if you've got this initial state where the orange neuron is really in sync and really communicating well with the green neuron, after what we call long-term potentiation, there's going to be more vesicles. More vesicles are going to release more neurotransmitters. There's going to be more receptors on the postsynaptic cell. So it's going to make that communication even more efficient. Now, there are a couple of reasons why long-term potentiation works and is really attractive as a model of memory in the brain. Not only is it making transmission more efficient, like how when you're texting someone, your conversation topics are really quick and efficient, it also occurs pretty quickly, and it can be pretty long-lasting too. This also occurs really often in the hippocampus. So if you remember back to our neuro lecture, remembering hippocampus is the source of memory. So long-term potentiation is the way that we enhance pieces of information in our brain so that it becomes easier to use them and we strengthen that memory. Remember when we talked about neurotransmitters too in the neuroscience chapter? So there are a couple neurotransmitters that are more involved in memory. The first is acetylcholine. So this is important for encoding new information. And we know that in Alzheimer's disease, for instance, neural circuits that use acetylcholine tend to be pretty degenerated. We know here, for instance, you can see in this cross-section of a patient with Alzheimer's, their hippocampus, their memory region, is kind of lacking compared to a participant with normal memory, as is their language regions. So they're physically losing gray matter in their brain that are responsible for encoding and processing these memories. So in general, if you have low acetylcholine, that means that it'll be hard to encode new information. And if it's too high, you might not consolidate or store it very well. The other neurotransmitter, though, is glutamate. So glutamate is really important for that long-term potentiation we talked about last slide, involved in creating more receptors or kind of influencing more vesicles. It's the thing that really strengthens that relationship between the two neurons.